So I want to pick up and talk about temperature effects. And I said last time as we were finishing up that change in temperature gave changes in dimension, and that's true but not complete. If it's restrained, you may not have changes in dimension, but then you'll have some strain. So I want to be a little more complete in our study of this and talk then about thermal strain. So thermal strain, we can talk about epsilon sub t. We'll say epsilon sub t is equal to alpha times delta t, where alpha is our coefficient of thermal expansion. Coefficient of thermal expansion. For instance, it's aluminum usually has a value that's somewhere around 13 times 10 to the minus 6. And the units on that would be 1 over degrees F. Steel, on the other hand, has a value of somewhere, depending on the alloy, but usually about 7 times 10. It doesn't change a lot with the alloys, but 7 times 10 to the minus 6, 1 over degrees F. So from this you can see that the units on this are usually going to be 1 over Kelvin or 1 over degrees centigrade, or maybe 1 over degrees F, or 1 over degrees Rankine, Rankine being the absolute portion of Fahrenheit. You'll use the same data point for this, because whether you're using Kelvin or centigrade, your delta T is the same, right? And you'll use the same data for this, whether you're using Fahrenheit or Rankine, your delta T will be the same. I didn't necessarily bring in the coefficients for the metric system. They'd be different numbers, because a 1 degree different centigrade is quite a bit different than 1 degree different Fahrenheit. So you'd have to look those up and deal with that. But these are some typical numbers for degrees Fahrenheit. You can see how, so if you heat aluminum up 1 degree Fahrenheit, it changes in dimension quite a bit more, or you have quite a bit more strain. We'll talk about how that affects the change in dimension in a moment. But you have quite a bit more strain than you do steel. This is problematic when they first started putting aluminum heads onto cast iron blocks. You had the cast iron block, it would heat up, and it would move a little bit, and then you had the aluminum that would heat up, the same delta T, same change in temperature, and it would move a lot more, and they had problems with head gaskets and things like that. They've got around a lot of that nowadays. They also have aluminum blocks, which avoid the problem altogether. But this is something you have to think about in design. Well, remember that strain, in general, was equal to delta over L. So if I set that equal to the thermal strain, I can say then that the change in dimension is equal to alpha times delta T times the original length. Okay. And that's going to have whatever units we put the length in. If we put the length in inches, it would have units of inches. If the length is in feet, it'd have units of feet, because the units on alpha and delta T should cancel out. Questions on that so far? Well, let's look at some cases here, or some possibilities. Let's say that we have something that's unrestrained. So we'll just take a cantilever beam or something sticking out, and we'll say that we have T naught, and we'll say that the stress is equal to 0, and we'll likewise say that the strain is equal to 0. And then I'm going to heat this thing up. So we'll look at this, and presumably this would get longer with temperature. So we'll have some T final that we could say was greater than T initial. And it's going to get longer, so we could say that epsilon sub T is certainly not equal to 0. The strain is changing, its dimensions are changing. But the stress, sigma, would be equal to 0. Of course, sigma, remember, sigma is equal to force divided by area, there's no force pushing back on that. It's allowed to get longer or to get shorter without having any force on it. It looks like it's got shorter. Maybe the temperature got colder. So anyway, I don't know. The other case we might look at is a little more involved. What if we have something that, I got a couple cases here. Let's say that we have something that just fits between these two supports. Okay, so we just slip the specimen in here and it just fits between there. So we'll have some T naught, and sigma sub t is equal to 0, and epsilon sub t is equal to 0 initially. And it just fit between there. And we're going to say that these supports don't move at all. That's the proverbial between the rock and the hard spot. And then we're going to heat this thing up. So we're going to look at T final being greater than T naught. And because it's between those two fixed points, between the rock and the hard spot, it doesn't get any longer, right? Those pieces don't move out of the way. So what would the strain be? Epsilon t. Well, remember that strain in general is equal to delta over L. Was it allowed to get longer? It wasn't, was it? So we know that the strain is equal to 0. But what about the stress? Certainly not equal to 0. You can imagine a tremendous amount of stress in there, right? I mean, this happens with railroad tracks quite regularly. Usually we see more derailments in the summertime because they take this long section of track like this, and it's probably pretty well fixed at this end, and pretty well fixed at this end, and particularly around corners, sometimes this can be a problem. And they heat it up, and what does the track do? It actually buckles like this. Okay, it'll just push out of the way like that, which is probably not good for running a train down at 60 miles an hour or 70 miles an hour, right? Okay, so tremendous stress. We're going to probably have buckling or something like that. Well, another case might be if we combine these two. The first case here was where it was completely free. The second one here is where it just fit in, is constrained. And then the third case is a little of both. So we take this piece and we put it in here and we leave a small gap, but not very big. And we know that we'll start out with some initial temperature, and sigma sub t is equal to 0 and epsilon sub t is equal to 0. And then I'm going to heat it up. And we'll heat it up enough that it would like to go well past this point. Okay? So it's going to come up and hit that, and it would like to go past that, but again, it's a fixed object, and it can't go past that. So we'll have something then that looks like this. And here, if T final is greater than T initial, we're going to have some epsilon T, right? It got longer, didn't it? Yeah, so we can't say that the strain is equal to 0 because it got longer, it closed that gap. And how about the stress? Well, it not only closed the gap, but it would have liked to have gone further than that, so we have quite a bit of stress in there, so we could say that sigma sub t is certainly not equal to 0. I should probably put a t on that one up there. Okay. Well, these two cases, case 2 and case 3, are actually statically indeterminate. Case 2 and 3 are statically indeterminate. But from our work last time, we can actually deal with statically indeterminate problems. So that should not be a big deal. And this brings us back to the comment that I made last time as we were finishing up, that change in temperature gave us a change in dimension. Well, that's true sometimes, right? I mean, when we looked at the first case, we got a change in dimension. Okay, I should probably draw this a little bit. It got quite a bit longer. Okay, but in, for instance, this case up here, did we get a change in dimension? No. So maybe I should say and, or, because it could be both of them, change in stress, right? If it's restrained, it's not going to change in its dimension, but it's going to change in its stress. So this is going to be a big deal when you start building stuff. You can have thermal strains and then use that to your advantage, or end up having a lot of trouble with it. Well, what I'd like to do is I'd like to look at this second case here. I'm going to go back and look at this in more detail. Okay, and see if we can tackle that and deal with the statically indeterminate portion of it. Questions before we do that? So I got some examples we'll look at in terms of practical examples of this thermal stress and thermal strain. But train rails are a big one. I don't know that it gets, probably if you go up in Canada, maybe it gets cold enough. I know in Russia they used to have a lot of trouble with this because they have very long rails, and it gets very cold in parts of Russia. I guess I've said this about the train rails here. This is if it gets hot, right? What happens if we take this up here and it gets really, really cold? So we lay out our tracks when it's nice weather, and then it gets really, really cold. They get shorter, right? Yeah, and they would have problems where the tracks would be like this, and there would be 4 feet or 6 feet of track missing, which is again a problem for a train going 60 miles an hour, right? Okay. So.
Wouldn't that bring up the treated wood underneath the rails too? Wouldn't that bring up the wood with it?
Well, as far as the rails go, like in this example here, the rails usually just slide sideways with it. Okay, I don't know about this. It's probably going to pull away from the wood attachment. The wood attachment is not all that great. If you look at the way rails are put together, it's a little scary. But they've worked for many, many years, so I shouldn't talk bad about them. Other questions? Or if you think about how many time zones do we have here? 3 or 4 across the United States. What's Russia have? When I was in school, it was 11, but then they got smaller, so I think it's 9 now. So it's a big piece of land. Anyway, let's go and look at that example. So we're going to again take these 2 fixed points here, the proverbial rock and hard spot, and we're going to slide that specimen right in between there. It just barely fits. It just slides in very nice. And we'll say that this is length L, and we're going to say no initial stress or strain. So no initial stress or strain, and we heat it some delta T. So we're going to heat some delta T, and we'd like to find the final stress. So find final stress. Okay. So we said that this was statically indeterminate, right? But we know how to handle those problems. Now we're going to release it. So if it's released, that would be to take off one of the supports there and just let it run free, so to speak. Okay? And how much longer would that get as we heated that up? Well, that would be delta due to thermal effects, which we said was alpha times delta T times the length, right? But we said it's not allowed to do that. So the reason it's not allowed to do that is you have a force pushing back on it. And that force pushing back on it, we could talk about some force P, and it's pushed back, it's compressed it, this distance here, which is going to be equal to what? Remember our old friend in general up here, delta is equal to PL over AE. Remember that one? We use Hooke's law to come up with that. So I could say that this delta was equal to PL over AE. And this is actually a compression, right? I think we agree that it's compression, so I could put a negative sign there indicating compression. And our compatibility equation would be to say that those are equal to each other, that alpha delta T times L would have to be equal to minus PL over AE. So when I go to solve that, I could talk about, let's see, P over A being equal to alpha times delta T times E, right? I get to cancel an L off of both sides. I get to cancel that L off of there, multiply both sides by E. I better have a negative there. Well, what's P over A? I guess if we have another general equation here, sigma is equal to P over A, isn't it? So that's the stress. So we could say that the stress, that's what we're looking for, is equal to minus alpha times delta T times E. Now alpha times delta T, that's going to be a unitless quantity, right? Because the units are going to cancel out on those. So whatever units E have is the units that stress have, and that should work because E is oftentimes PSI, so we'd expect the stress in PSI. Again, this negative here is from compression. Even if we had missed that up there, we'd have to recognize that it would be, in this scenario, under tremendous compressive stress. Questions with that? Yes?
Would it E change with temperature as well?
Yeah, E's going to change with temperature. Yeah, so we'd have to deal with that, or hopefully it doesn't change too much and we can just take an average. But absolutely, E's going to change with temperature. Yeah. So. Other questions? Yeah, there was a senior project. When I was in school, I had to do senior projects, and one of the students at OSU had a big etymology program at the time. I don't think they do much with etymology anymore, but that's bugs, and probably a certain type of bug. So anyway, but bugs. That's why I turn the comments off on these videos, right? So people don't have to write me and tell me about different types of bugs. But it's bugs. So these students got this project, which seemed pretty grim to me. But their task was to find the some mass properties of these bugs in terms of center of mass and things like that, and trying to figure out how to make walking machines from these bugs. And bugs are fairly uncooperative with that, so they would cool the bugs down so the bugs would stay nice and still and whatnot. And then they had a spring system to try and make some of these measurements. And the question came up during their final presentation, did they calibrate their spring at room temperature or at the reduced temperatures when they were trying to measure the cold bugs? And they didn't calibrate it at the reduced temperature. So it was kind of one of those things where it was a question they definitely did not want asked. And kind of just everyone sat there silent. It was not good. So absolutely, E can definitely be a big function of temperature. Questions? Okay, well, let's try an example then. Maybe a bit more practical example than bugs. Well, let's say we got a warehouse and we've got a gutter on the side of the warehouse, so we call some people out to install one. So we put an aluminum gutter. So we got this aluminum gutter. It's installed on a warehouse at 30 degrees Fahrenheit. The warehouse, we're told, is 300 feet long, so we put the gutter on there. We'd like to find the delta, the change in dimension, in the summertime when it warms up to 105 degrees Fahrenheit. We're told that for aluminum, we'll take alpha, as I mentioned earlier. We just take it as 13 times 10 to the minus 6. It doesn't change with very much with aluminum alloys, so we'd probably be pretty good with that. And that will then be 1 over degrees Fahrenheit. So my equation then would be that delta is equal to alpha times delta T times the length. So I could say that this was 13 times 10 to the minus 6 times 1 over F. And then the delta T, what's that going to be? 75 degrees F, and then the original length 300 feet. So I get to cancel that with that, and we come up with 0.29 feet, which is maybe a little hard to recognize. That turns out to be 3.51 inches. Okay, that changes quite a bit. 3.5 inches. So is this contrived? Let's see. Do we have aluminum gutters? Yeah, aluminum gutters are nice because they don't tend to rust out very much. So we definitely have aluminum gutters. Ever put gutters on at 30 degrees? Yeah, put them on in the wintertime. You can do 30 degrees. Sometimes that's a good time to work. It's usually cold but not raining. The trades tend to work a little cheaper in the wintertime. So a lot of people get some of their maintenance done if they can during the wintertime. So no problem there. How about the summer? 105, does everybody get 105 around here? Well, remember where your temperature, when the weather comes on and they give you your temperature, that temperature is actually measured where? Well, the airport, but where at the airport? Usually in the shade. Okay, when they say, oh, it's going to be a scorcher day, it's going to be 102, that's actually in the shade. So if you go out and measure the temperature in the sun, it'll be quite a bit higher than that. So you look up on the side of that building, 105 is not unreasonable at all, even for a fairly temperate area where we are. So I think these are very reasonable numbers, and the gutter is going to stretch quite a bit. So how do you deal with that? Well, you could put an expansion joint in there to try and deal with it, or you could figure that you're just going to nail it to the side of the building enough that it's not going to be allowed to stretch, right? The other thing that's happening at the same time is we might think, well, how are we going to deal with this gutter getting 3.5 inches longer? What is also getting longer through this process? The building itself, right? Maybe not as long as the aluminum gutter, but it may be getting longer too. So some things to think about. Questions with that? Well, at this point, there's some interesting practical problems that we can talk a little bit more about. I think we've talked some about train tracks and how if you have a very long straight track that's essentially constrained and the temperature increases, so our temperature goes up, the track, the rails are going to try and get longer, and oftentimes you can get buckling. This can be a problem. Of course, the other way can be a problem too. The temperature drops tremendously and actually tear the track apart in places where they have very long runs of tracks. That can be problematic. Usually, there's natural things that help with this, and that's just curves in the track. You have a general curve in the track, and then the track, if the temperature increases, is just going to push out slightly in the gravel bed, and usually is not a problem. So this also happens with steam pipes, very long steam pipe. They'll have to put a bit of a curve into it, an expansion joint or something like this. Well, this phenomenon of this curve just expanding harmlessly on the track, I saw an interesting example one time where this didn't happen so harmlessly in terms of a street. So they had a scenario where you had a street here in a neighborhood, and this street was on a curve, and as the temperature heated up, this street tended to push out this way just a little bit, and the driveway was then bearing against the street, which was bearing against the house slab. This was in the southeast part of the United States, where they had a slab on grade, where you have a concrete slab, a little more like commercial construction around here. There's no crawl space under there. So essentially they have a driveway slab, and then you have a house slab, and this ended up pushing on the house slab and ended up cracking the house slab through there. Before they were done, they had a 2 or 3 inch crack through their slab. So that's not super common. A lot of times there'll be enough expansion joints in here, or the geometry is not such that it pushes just right. But it's something to think about. Unconstrained expansion can tend to be a problem. So it's always hard to figure out who would be responsible in this case. Everyone's going to be pointing their fingers at one another about whether they put enough expansion joints in, or if the street should have moved. Hopefully the street doesn't move enough to now be on someone else's property. But anyway, something to think about. And before we think that just the civil engineers get all of the fun in terms of thermal expansion with streets and bridges and railroad tracks, we've got some interesting mechanical problems too. What if you have a a pulley or a shaft. Let's see. So, and you have a bearing or a pulley or a gear that's on that, and it fits. It's supposed to be an interference fit, and you don't have a big press to put it on. What can you do? Yeah, you're going to heat this up, right? And you're going to cool this down and slide them together and hope that you get them together before they come to the same temperature, because then they're stuck for good, right? They also do this in the reverse. If you look at a engine block with a lot of industrial engine blocks will use sleeves, and there'll be a wet sleeve or a dry sleeve. I guess that's 3-cylinder there. And they'll have these sleeves that, particularly if they're a dry sleeve, they're going to slide in. Let's see if I got that right. There we go. Okay, and it's going to be an interference fit. Really, the only thing that holds it in there is the interference. So what do? We roll the block outside on a nice, warm, sunny day and get this thing hot. Okay, and what do we do with the sleeves? Yeah, put them in the freezer, get them cold. Okay, and then don't waste any time getting them in there. So this is used quite a bit. And again, this we can use this to our advantage. It sometimes can be difficult when we look at an exhaust manifold or something like that. It will expand more than what it's bolted to and break the bolts. Really high-quality industrial engines usually have some sort of a clamping mechanism rather than actually just bolting it down. There's an interesting example if we look at thermal stresses, the Liberty Bell. This is out of a machine design book. It says the Liberty Bell, cast in 1753, is actually cast in 1752 and then recast, that was in London, and recast twice in Philadelphia. So it's had a checkered history a little bit. It cracked twice when they tried to ring it to begin with, so that's why they had to recast it twice in Philadelphia. So it's hard to say exactly when they were thinking about it was cast, but cast in 1752 and 1753. Has residual tensile stresses in the outside surface because the casting cooled more rapidly from the inside. I don't know if we have any people that specialize in making bells in here, but if you're going to cast a bell, you usually cast the bells upside down. So you'll build a form like this and cast the bell upside down. So this is going to remain quite a bit hotter in here, and this is going to cool down quicker like that. Okay. So has residual tensile stresses in the outside surface because the casting cooled most rapidly from the inside surface. The principle that what cools last is in residual tension. Okay, so you've got tension on the outside surface. After 75 years of satisfactory service, the bell cracked probably as a result of fatigue from superimposed vibratory stresses caused by ringing the bell. Attempts were made to arrest the crack growth by drilling holes at the ends of the crack, and further crack extensions subsequently occurred. And your author cites this as proof that residual stresses are still present in the bell, which is kind of cool to think that the stresses that were in that bell in 1753 or 1752 are still actually there. How many of you have gone to the Liberty Bell and looked at that? Okay. You see where they drilled the holes and put in the pins and tried to arrest the crack? Yeah, and the stresses are actually still there. I always think that's kind of neat that stresses could hang around for a few hundred years. While you were there at the Liberty Bell, did you look at the inscription on the Liberty Bell? What was the inscription on the Liberty Bell? It said, "Proclaim liberty throughout all the land and unto all the inhabitants thereof." I guess that's why they call it the Liberty Bell. Where'd that come from? No takers on where the inscription on the Liberty Bell came from? Let's see, 1752, 1753. Please don't say the Constitution. No one? It's actually from Leviticus, the Old Testament, Leviticus 25:10. So that usually catches people off guard. So, yeah. Anyway, so I always think the Liberty Bell is a really interesting example of thermal stresses, because those stresses are still there from the day it was made. So they'll last hundreds of years unless something else removes them. Yes?
But, I mean, definitely by now, the bell should be the same temperature all throughout. How are the stresses, how are they still there?
Yeah, but in the material. A lot of times stresses will end up staying in something. If you do a lot of work on something, you drill a bunch of holes or something, you can end up having stresses and they will stay in the material. Yeah. And it probably cracked because the process of ringing the bell introduced yet more stresses on top of those and superimposed those. Although it sounded like a little dicey from day one that it cracked twice already. So probably should have got warranty on it from London, but that probably wasn't going to happen at that time. So, other questions? So we've got hopefully got thermal stresses pretty well taken care of. I'd like to start to look at how we can quantify and talk about general stresses. So let's talk about some general stress state. So one thing, I guess, talking about the thermal stresses and the Liberty Bell and whatnot is maybe you've heard someone talking about, well, this is a really fancy thing. It's been shot peened or something like that. That's usually a process of trying to get the stresses out of it. So I'm mentioning that stresses can be remain in it from manufacturing and whatnot, and they'll try and relieve those stresses. And one way of relieving those stresses is shot peening. They'll actually just like sandblasting, but they'll do it with a larger shot. If anyone's ever been around where they're trying to weld cast iron, they'll actually, sometimes you can just take a hammer and hit it as it cools off and try and relieve those stresses. So there's ways of trying to do that, and sometimes you're successful and sometimes you're not. Well, let's look at a general stress state. So let's take a body here, and I can apply some forces to this thing. They could be in tension, or they could be in compression. We could even apply some moments to it. If you wanted to put concentrated or distributed loads on this, you could. And what we're going to do is we're going to look at a small element on that thing. And if I look then at a coordinate system here, and look at this element, I'll draw this a little larger because it'll get a little cluttered before I'm done on that element. So I'm going to say that this is the y direction. I'm going to say that this is the x direction. I'm going to say that this is the z direction. Yeah, we've got a right-hand coordinate system, so we're okay. So we could start to quantify these stresses, and we might talk about the stress out of this space. We could say that that is sigma z. Okay. And there would likewise, I can't really put it back here, but there would likewise be one in the minus z direction, so that this thing's in equilibrium. I could put one over here. We could say that this is sigma y, and likewise you would have one back here in the, not sigma y, sigma x. So we've got sigma x here. So we've got sigma x, and we would have one going this way in the negative x direction. I'm not going to put it there, but we would. Here we've got sigma y, and we could have one down. So we'd have them off of both the positive x direction and the negative x direction, or positive y direction and the negative y direction, so it's in equilibrium. So those would be the normal stresses. Remember, sigma, that's defined as normal stress. Okay, and then tau, that was shear stress, right? So we could talk about shear stresses, and there would be shear stresses on here. I would have shear stresses like this, and shear stresses like this, and like this, and like this, and like that. And I've actually only drawn half the shear stresses. There would be that many more shear stresses on the faces that I don't see. And it's not coincidence that I drew these, and these arrows actually point to each other. We do that so that it's again in equilibrium, so we don't start this thing rotating. Okay, so this one in this direction and that one in that direction, keep it from rotating. So we could say that this one is actually equal to that one. I guess I better name them before I do that. I could say that this was tau on the z face in the x direction. I could say that this is tau on the x face in the z direction, and we could of course then say that tau on the z face in the x direction has to equal tau on the x face in the z direction. This is going to be tau on the z face in the y direction, whereas this will be tau on the y face in the z direction. This will be tau on the x face in the y direction, and this will be tau on the y face in the x direction. And we could say that, of course, tau on the y face in the x direction had to equal tau on the x face in the y direction, and that tau on the z face in the y direction equals tau on the y face in the z direction, for those to be in equilibrium. Okay? So that's how in a 3D element I could put down or represent the normal stresses and the shear stresses. And some of these may be zero, but if I were to look at all of those. Now what I'd like to do is probably control this a little more and look at something initially that's a little easier to look at, and that's a 2D, or what we call plane stress. So are there questions with this? So let me go on and look at plane stress then. So with 2D, or what we call plane stress, we're going to require that sigma z is equal to tau on the z face in the x direction is equal to tau on the z face in the y direction, that those all be equal to 0. So what does that look like on this piece? That this one is 0, that the z face in the x direction is equal to 0, and the z face in the y direction is equal to 0. Well, if these two are 0, then this one would be 0, and this one would be 0, right? So I'm left then with sigma x, with sigma y, and tau xy and yx, which would be the same. So let me draw that, and I can draw this on a two-dimensional element that's a lot easier to look at. And I'm going to say that I have my x direction here and my y direction here. So I'll put sigma x, and now it's a little easier to see that there is indeed going to be one this way. That will also be sigma x. And I could say that I have sigma y and sigma y. And then I need to talk about these shear stresses. And since they're the same, all those arrows are the same value, I'm just going to call that tau xy. I mean, that has to be equal to, same as, tau yx. So this is our plane stress, and we'll use that a lot as we describe things, and eventually as we talk about Moore's circle. Questions with that? Well, let's say then someone gives you some stresses. So let's say that you're given sigma x is equal to 5 megapascals. Sigma y is equal to minus 3 megapascals.
Didn't you say that tau z on the z plane in the x direction is equal to tau on the x plane?
Did I say what? Tau on the z, zx?
Yeah, zx is equal to xz.
Uh-huh.
And then on the previous, on the page on that, you got zx equals to zy.
Well, they're equal to 0. Yeah. I mean, so I could go further with this if I wanted to. Then, I mean, this is, therefore, with this statement here, we would understand that tau xz is equal to 0 and tau yz is also equal to 0. Good? So I got sigma x and I got sigma y defined, and we'll say tau xy is equal to minus 2 megapascals. Okay. So I'd like to represent that on an element. Okay, sometimes we talk about a stress cube. This is a two-dimensional stress cube, so it's really flat. I'd like to put it onto this element. Okay. So I'm going to do this a couple times. I'm going to use these numbers and I'm going to fix it up a little bit. We could go ahead and say that this is the x face, this is the y face. So we're saying on the x face we have 5 megapascals. So there is 5 megapascals. And then the y face, I could go ahead and we've always drawn this positive, so I'll drop positive and I would have minus 3 megapascals. And then on the x face in the y direction, let's see, x face in y direction, right? This is the face, and this is the direction. So on the x face in the y direction, that is to say this, and then these others would have to follow suit for it to be in equilibrium, right? We would say that this would be equal to minus 2 megapascals, right? Okay, I don't like those negative signs floating around, so I think what I will change this to, I mean, technically that's correct, but I'm going to say that this is better, is I can get rid of the negative signs. I can't just wipe them away, but if I change the direction of the arrow, I can get rid of the negative signs. So this 5 megapascals, that's not a problem. And then the 3 megapascals, that being negative, that is a problem. So let's see, instead of having to write that negative sign, I will turn the arrow around. And we can write this as 3 megapascals. Okay. And then this shear is also a problem. On the x face in the y direction, well, if it's on the x face in the y direction, if I put the head of the arrow down there, I can get rid of the negative sign, right? And that means that these are then going to follow suit. And I would have this tau, or I guess I'll just write the, I'll just write that as positive 2 megapascals, so 2 megapascals. Okay? So I get rid of the negative signs and represent those directions with the arrows. And then it becomes very easy to see. It looks like in the x direction we have tension. In the y direction we have what? Compression. Yeah. And then the shear is a little harder to work out. We're going to see that of course, has to do with the angle and which way it's racked. But that gives us a very nice starting point. Well, where we will go next time is take what we've learned here and start to ask the question. I mean, if you have this specimen that is loaded, okay, and we've talked about putting the stress element like that, you could come up with some force in the y direction and the x direction. What happens if we look at a different orientation? What's it going to do? Could we get different stresses? And the answer is yeah. So it'll be important for us to look at those different orientations, and that's what we'll do when we get together next time. Also, make sure you're ready for the quiz. Take care.